All right, so today I just want to talk a little bit about what organic chemistry is, why we should study it, and what are some of the ways that we study it or ways that we break down the study of organic chemistry. Um, so before I do that, I do want to get into this question of what we call the course, because it actually varies geographically, and I think it might be interesting to like really map it out. But just to paint with broad brushstrokes, generally here on the East Coast, particularly in the Northeast, we call this course Orgo. And that's what I will call it. That's what I came up calling it. So organic chem will always be Orgo to me. And when I like write, instead of writing out organic chemistry resources on the cabinet over there, I wrote Orgo resources. Um, that's just what I call it. On the West Coast, it would be called OChem, not Orgo. So pretty much everywhere on the West Coast, if you take organic chemistry, you're taking OChem, which has some logic to it because most of us, even on the East Coast, call physical chemistry PChem. So, they have a little more consistency. And then in the middle of the country, it might be called either one or it might just be called organic. There's, as far as I can tell, not consistency in the middle of the country. Kind of depends. And I did hear at least one report that up at McGill they just call it org. So I don't know. The point is, I will call the class Orgo all the time. Um, but when you talk to people from elsewhere, they might think that's weird. Sorry, those people are just weird. Um, so how do we define it? Some of us already mentioned it's the chemistry of carbon-based molecules. Now, how did carbon become organic? Like, how are those two related? Well, back in the 18th century, when chemistry was just getting started, chemists kind of classified molecules as, all right, does this come from living things or does it come from non-living things? So things that came from organisms became called organic, and things that came from, that didn't come from organisms were called inorganic. And the theory really went that there's something special about life. So molecules that come from living things have some special vital force, some special life force that's just part of the molecules, and things that were inorganic just didn't have that life force. Well, in the early 1800s, chemists started to actually go into the lab and take inorganic compounds and synthesize them into organic compounds. So the first organic compound ever synthesized in the lab was a molecule called urea. It looks like that. Does anyone know where you might find urea? Urine, yeah. So does that come from living things? Yes. So urea was definitely an organic compound, but then a chemist went into the lab and made it without any living things, other than him putting stuff into the jar. He was the living thing present. But that kind of blew up this theory because now urea must not have this vital force because you could make it from non-living stuff without putting it through an organism. So this really became irrelevant when you could start synthesizing organic compounds from inorganic compounds. Later on, as atomic theory developed, I mean, when this happened, most of the elements hadn't been discovered yet. Atomic theory was just in its infancy. As atomic theory developed and people realized, okay, molecules are made of elements, and what element keeps showing up in all these organic compounds, it was carbon. So it turns out carbon is the special element, the one that makes all these organic compounds that pretty much every living thing is based on a bunch of organic molecules providing structure, and then a lot of, there are some inorganic compounds as well, and there's definitely water, but the organic compounds, which are based on carbon, provide the structure for every living thing. So I don't want to get into a question of, well, is such and such organic, is such and such not organic. We'll say if it's got carbon, it's probably organic, with the exception of really small, simple molecules like carbon dioxide, sodium carbonate, calcium carbonate. Those, even though they have carbon in them, they're generally considered inorganic. But the everything we say about organic compounds in this class will still apply to molecules like CO2. So it's not really an important distinction. So this is really going to be a class about carbon, molecules based on carbon. So that kind of begs the question, how did carbon get to be so special? Right? We have this whole branch of of chemistry called organic chemistry, and that's just all about one element, or mostly about one element. So what's so special about that one element that gives it its whole branch? Like, why don't we have whole courses devoted to the chemistry of, I don't know, fluorine, or whole courses devoted to the chemistry of sulfur? I would think of it in terms of three different properties. So the first one is the number of bonds that carbon atoms make. I don't expect everyone to remember everything from chemistry. It may have been 2 years since you took it, and even if you took it last year, it's been a whole summer. But some of you may remember. The periodic table gives us some trends in how many bonds things tend to make. So if we go across this top row of the periodic table, first of all, why would I focus? I have focused solely on elements on the upper right-hand corner of the periodic table. Why would I focus on those? They're not metals. So they're the ones that make molecules. All the metals don't make molecules. Sometimes metals can get incorporated into molecules, but generally you can't make molecules out of just metal atoms. So we're looking at the nonmetals, and anyone remember how many bonds boron tends to make? 3, all right. Carbon, 4. Nitrogen, not 5. 3. It starts going down again. So it's actually boron makes 3, carbon makes 4, nitrogen makes 3, oxygen 2, fluorine 1. If I go down to the next row and I start with silicon, for oxygen I did another O. Silly me. So oxygen makes 2. If I go down a row to silicon, so silicon makes 4, phosphorus 3, sulfur 2, chlorine 1. So we can see, carbon kind of stands out here because it makes more bonds than most of the others, except for silicon. Because of that similarity between carbon and silicon, people have often speculated about silicon-based life forms rather than carbon-based. Although there are good reasons to believe that it's more challenging to build a life form on silicon. At least that comparison. They both tend to make 4 bonds. That's intriguing to people. But carbon makes 4 bonds. Why is that important? Well, if you want to build up big molecules, you want to be able to put together lots of atoms of carbon as a backbone. And since carbon makes 4 bonds, when you make a chain of carbon atoms, each one in the middle has 2 extra spots to glue something else onto the molecule. If you tried to do the same thing with oxygen, which makes 2 bonds, you look anywhere in the middle of that chain, how many extra spots do I have to glue something onto oxygen? 0. All right. So making 4 bonds is important because it gives you the ability to build a chain and actually hang stuff off of it. Okay. So that would be the first thing. Second thing, yeah, question? So the question is, what about atoms that can make more than 4 bonds? Why don't we build big molecules out of them? So you may have never even seen atoms that can make more than 4 bonds. If you've only had 1 year of chemistry, you probably didn't talk about them. Sometimes you can have atoms make 5 bonds or 6 bonds, but it's in these rare exceptional cases. So when you see an atom make 5 or 6 bonds, it's generally because it's bonded to something super electronegative like fluorine. And fluorine only makes 1. So for instance, a molecule where phosphorus does break the octet rule and make 5 bonds would be PF5. And in a case like PF5, there's a response to question about more than 4 bonds. In a molecule like PF5, you're convincing phosphorus to make more than 3 bonds by reacting with fluorine, which is super electronegative, which really can bully other atoms around. And so fluorine bullies this phosphorus into making 5 bonds. But you'll notice since fluorine only makes 1 bond itself, there's no way to expand that molecule either. So most of the time, molecules that have what we call an expanded octet, molecules that make more than 4 bonds, that's it. They're relatively small molecules because of the atoms that are around the outside. And if you've never seen molecules that go over an octet like this, that's okay, because in organic chemistry, we never see them. So you can forget, you can ignore what I'm talking about right now. Another question? Could you have a chain of boron? The answer is yes, you can have a chain of boron. There are molecules called boranes that are based on boron. And there's kind of a rich chemistry of them, but they're still much more limited than carbon compounds. So we'll talk about some of the other distinctions besides number of bonds. But so you can make molecules of boron and hydrogen, particularly. These molecules tend to be small. All right, so carbon forms 4 bonds, but what distinguishes it from, say, silicon? Second factor would be, well, how good are the bonds that it forms? Turns out carbon forms really strong bonds to itself compared to other elements. So these are bond energies. Bond energy is really just a measure of strength. And so I looked up, all right, what is the bond energy for bonds of various elements, atoms bonding to other atoms of the same element? And what do you notice in this list? Yeah, carbon-carbon bonds are especially strong, right? So not only can you form lots of bonds between carbon atoms, but those chains are going to be relatively stable. It's going to be hard to break them up. If you form silicon-silicon chains, they are, only 2/3 as strong, or a little less than 2/3 as strong. So it's going to be easier to break up those molecules you make based on a silicon-silicon chain. So there's number of bonds, there's bond strength. And then the third thing would be ability to play nicely with others. Someone brought up the idea of electronegativity. Electronegativity, you may remember, you may not remember from your first year of chemistry. Electronegativity really measures how strongly an atom attracts electrons. And turns out carbon is kind of medium in electronegativity, which means it plays nicely with lots of other elements. It gets along with other elements. It's not too, harsh as a bully like oxygen or fluorine, where it's really hogging electrons from other elements. And it also just doesn't kind of give its electrons away when it bonds to something else. And that tends to make strong bonds with a wide variety of elements. So you'll notice these other bonds between similar atoms, boron, boron, oxygen, oxygen, all of these are below 300 kilojoules per mole. But if you look at carbon bonded to most other elements, it's 300 or above, meaning carbon makes relatively strong bonds not only with itself, but with a lot of other elements. It also can make double bonds and triple bonds, which adds to its versatility. So those 3 reasons I would point out is probably the 3 keys to why carbon is special among all the elements. First, 4 bonds is good for making chains. Second, relatively strong bonds means you're going to make stable chains. And then last, it plays nicely with a lot of other elements, which gives you a wide variety of possibilities for molecules. So carbon is what we're studying here. And it turns out it's not just a few compounds that you can make from carbon. Turns out it's in the millions. So there's a registry that keeps track of all the compounds that have been described in any chemistry journal article anywhere, and also keep track of how many chemicals are available commercially, how many you can actually buy from a chemical company. It turns out as of June, it was 164 million had been described, 104 were available commercially. Not all of those are organic, but a lot of them are. I think definitely over 10 million organic compounds, which means a lot of compounds. Now, if we were chemists 200 years ago, 150 years ago, the number of compounds that were known was really small, right? Maybe it was a couple hundred. And it might have been possible to just treat our subject as cataloging, okay, of these couple hundred molecules, compounds that are known, what does each one do, right? 200 is a lot to keep track of, but it's something you can keep track of. 10 million, 100 million, these are not numbers of things we can possibly even keep track of. What we should be doing is looking for patterns. So this quote here, I just put it, in a voice bubble instead. Learning organic chemistry is hard work. The amount of information is out there as close to infinite as makes no difference. The best solution is to make sure that we understand what we learn and develop a feel for the way molecules behave. So because carbon can do so much stuff, what I want you to do in this class is not try and look at each individual molecule and memorize what each individual molecule does. What I want you to do is look for patterns. Start to talk about molecules as if they're people or pets, or something that has feelings, something that has certain tendencies. I want you to really get a sense of, all right, how do molecules behave? And so that's what we're going to do. So that's what organic chemistry is. Now, why do we study it? How many people took some form of gas-powered transportation at school? All right, that's like 90% of us. How many people took some sort of their own powered transportation to school? All right, that would be the rest of us. That was powered by organic molecules as well. But gas is pretty much all organic molecules. Things like benzene, MTBE, and octane are up there. And you might look at those symbols right now and they make no sense to you. That's okay. They're going to make sense to you in a week or two. But energy is a huge challenge for us, and right now most of our sources of energy are organic molecules. How many people have ever used a plastic bottle? Yeah. So plastics are generally polymers, generally organic polymers. If you have a bottle that says peat on the bottom, it's this polymer, which is polyethylene terephthalate, something like that. It's basically this organic unit repeating over and over and over. Polycarbonate, polyester, nylon, Kevlar. These are all organic polymers. So organic polymers, kind of important to our everyday lives. They make our lives better. And in some ways maybe worse, but they're important. Can anyone identify this molecule? Given the hint. Chlorophyll, yeah, that's chlorophyll. So which one is it? I don't know. There's probably multiple variations. I just picked one. The point is, if you want to understand living things are made of these molecules. And so you need to understand how these molecules are made, what their structure is, how their structure plays into their function. And the more you understand organic chemistry, the more, awesome living things start to seem, because it's like this molecular dance among millions of different kinds of molecules. And each molecule has its own part to play in that molecular dance. And each part of the molecule is important. Like if you took chlorophyll, if you chopped off, any of the atoms in there, it might cease to function and the plant dies. And without plants, there's no us. So one molecule can be really important, and one part of one molecule can be really important. And so, if you want to understand life, you got to start by understanding the molecules that it's made of. And then I would say another important thing to think about is once you understand life, then you can start to think about, well, how can we manipulate living things? So, particularly ourselves, right? This here, Lipitor, does anyone know what that's for? Yeah, this lowers cholesterol. So this is a group of drug called statins. These lower cholesterol. And so if you want to lower someone's cholesterol, which will hopefully lower their chance of heart disease and keep people alive longer, so that's usually a pretty admirable goal. First, you've got to understand, well, where does cholesterol in the body come from? And you've got to study the organic molecules. What are the molecular steps that build cholesterol from smaller molecules in the body? And once you understand that process, then you can say, okay, how can I design a molecule that can go in and disrupt that process? Because so-and-so has high cholesterol. I want their body to stop making as much cholesterol as it's making. So I want to add in, essentially, some molecule that will go in and disrupt the process so that they make less. And so you can design a new molecule like Lipitor that will keep their body from producing as much cholesterol, lower their cholesterol, hopefully keep them alive. And then you need an organic chemist to figure out, well, how am I going to synthesize it? You might design this molecule in theory, but then you've got to actually go and synthesize it. And that's where organic chemistry are really needed. So understanding organic chemistry is really the key to a lot of cool things, I think. And so that's why I would say why we study it. And then last thing I want to talk about is, well, how do we approach it? How do most courses approach it, and how will we approach it in this class? So there's 4 main areas of study, which I would call structure, spectroscopy, reaction mechanism, and then synthesis. So structure is what it sounds like. It's, okay, what are molecules like? What are their shapes? How are the atoms bonded together? Where are the positive charges? Where are the negative charges? Where are the electrons? And then we're going to take it a level deeper. We'll get into what we call the orbitals that make up a molecule, the molecular orbitals. It's something that if you took AP chemistry, you heard the term orbital. We talked about orbitals, but we didn't really get into orbitals. And if you only had 1 year of chemistry, you might not have ever even used the term orbital. It's okay. It's this really complicated concept that we're going to distill down to something manageable, understandable. And that's all part of what the structure is. So in the structure part of the course, we'll be drawing lots of pictures like the ones up here. This one down at the bottom you can't necessarily see very well, but it's a picture of a pi molecular orbital in the molecule that's up above. Spectroscopy is essentially the practice of how do we take an organic compound and identify what its molecular structure is. If I gave you an organic compound and I put it in front of you, it would probably either be like a colorless oil or a white crystalline solid. Some of them would be colored solids or colored oils. But generally, just looking at it, there's no way to tell what's in it. So spectroscopy is this technique where there are lots of different spectroscopic techniques that we use, but it's the idea that we can take samples of the substance, run some analysis, get some data. We get data, pictures that look like these up on the screen, and then based on those, we figure out, oh, this is what the structure is based on those pictures. All right. So that's spectroscopy. Another branch is reaction mechanisms. So it's thinking about how reactions happen, what order do we break and form bonds, what angles the molecules have to approach each other, how can we speed up a reaction, how can we slow down a reaction, and then an understanding of reaction mechanisms really allows you to take two new molecules you've never seen before and make a prediction about what's going to happen when they're mixed together. And if you get that, then you really have the key to understanding all of organic chemistry. Here's just an example of what a reaction mechanism looks like. This is actually the mechanism of what we call the Hoffman rearrangement, which you look at this right now, and it probably just looks like this crazy gobbledygook of drawings with some arrows on them and everything. But I promise you, in a few months, you'll look at this and you'll be able to understand what each of these arrows means, what each of these structures means. And maybe by the end of the year, depending on how fast you move through the course material, some of you might not get to this point, some of you will, but you might be able to look at this and follow along, and then you get to this step down here, and you might say, oh, the rest of this all makes sense. That step is really weird. If you can get to the point where you look at this and you're like, oh, all this really makes sense. Whoa, what's going on here? Then I'll really know that you understand reaction mechanisms well. But right now, this just probably looks like the whole thing is kind of crazy. But I swear you'll be able to interpret that whole thing. And then the last piece of organic chemistry is synthesis, and that's the process of taking commercially available compounds and putting them together to make a target molecule. So let's say you work for Pfizer and you just designed the next Lipitor, the next generation of cholesterol drug. You would then need to come up with a way to produce it, because you can't sell it if you can't produce it. So you need to take smaller molecules and build them up. And so that's the process of synthesis. Now, here's an example of a synthesis. This is for a drug, I believe, called quiactin, but I forgot to look up exactly what it does. But you start with simple molecules. You can, even if you don't understand what these pictures mean, you can tell that this thing up here is relatively simple compared to this thing down here, which is more complicated. And if you find synthesis interesting, there's this free app put out by a professor at the University of Arizona, I think. It's called Chemistry by Design. If you just search it, you can install it on your phone, and it has like 1,400 different syntheses in it, and you can just flip through them. I do this sometimes in my free time, and my wife just makes fun of me for it. But synthesis is really cool. This is where the really interesting problems in organic chemistry are, the really big challenges, and probably the most intellectually stimulating. But we're not going to focus on synthesis, and the reason is, to really do synthesis, you need to understand, you need to know lots and lots of reactions, right? It's about using known reactions to carry out a synthesis. Well, you need to know lots of reactions before you can do really interesting synthesis problems. And I don't want our focus to be, okay, let's cram reactions into our heads. So a lot of college organic chemistry classes, what they do is they do all four of these things mixed together. And people get tripped up by individual parts of it, but then that causes them to, it causes a domino effect where you get tripped up by maybe synthesis, and then that hinders your understanding of mechanisms, and then it hinders you, then you're too distracted to do spectroscopy right. And I want us to be more focused. So we are going to focus on structure and mechanism in this class. Structure, everyone's going to start with structure. Our first 10 modules are all about structure. Really getting to know molecules. And then after that, most of the rest is going to be about mechanism. But if you think at some point you're like, you know what, I'd like to learn a little bit about spectroscopy. Totally, you can learn some spectroscopy. That's going to be optional for us. And likewise, if you want to do synthesis, you can definitely do synthesis once we've learned enough reactions. You have to kind of get to a point where you know enough reactions before you can do synthesis. It's kind of like playing chess, except instead of how many different kinds of chess pieces are there? 7, 6. Instead of like 6 or 7 different kinds of pieces that each moves in one or two specific ways, it's like playing chess where there are like 500 different pieces and each one can move like 20 different ways. That's what synthesis is like, and I don't want you worrying too much about learning all those different moves. So that's why we'll focus on structure and mechanism. But you can definitely do the others if you want. All right, thanks for your attention today.